Hello and welcome back to another LeetCode video. Today we're looking at the LeetCode 778, Swim in Rising Water. This is the daily problem today. And it's very nice because I think it falls into the category of graph problems that we've been practicing lately. So let's have a look at this. This is a hard one. And we're given an n by n integer matrix where each value in the grid represents the elevation at that point. It starts raining and the water gradually rises over time. At time t, the water level is t, meaning any cell with elevation less than equal to t is submerged or reachable. You can swim from a square to another four-directionally adjacent square if and only if the elevation of both squares individually are at most t. You can swim infinite distances in zero time. Of course, you must stay within the boundaries of the grid during your swim. Return the minimum time until you can reach the bottom right square. We start in the top left and we have to reach the bottom right square. Within the boundaries of the grid. No, sorry, I jumped. Bottom right square. If you start at the top left square. Nice, cool. So, right, here's an example. So we start here. The elevation is 0. At time 0, you are in the grid location 0, 0. You cannot go anywhere because four directionally adjacent neighbors have higher elevation than t equals 0. You can reach point 1. You cannot reach point 1, 1 until time 3. So I guess at time 1 we can reach elevation 1, at time 2 elevation 2, and at time 3 elevation 3. So that's what's our output going to be. And okay, this is another interesting example. Just copy that, put that into our little drawing board so we can draw on it. Right. So, okay, so if we look at this, actually, I want to move it again. Yes. So we start here. This is going to be our start, and this is going to be our goal. At time t, we can reach this location at 1. Right. So they drew the path in here that leads to the solution of 16. And what you can see here is that we follow this path until we reach t16. But because 15 and 14 are all smaller, that means we can instantly swim towards the goal. Because we can cover infinite distances in 0 time. So I'm thinking we should use, I guess, it's yeah, like I said, it's probably classic graph traversal problem. Except now we have different conditions of when we can go to another node. We used to look at, is the neighboring cell a land or a water? That was a condition that we had in some of these problems. We had the condition that we could only walk upwards. That was the Atlantic-Pacific rain problem. And now here we can swim anywhere if a time ticker value has a value that is the same or higher. So I'm thinking we might just have to change our queue. How do we process these elements? We know that we can reach, well, what if we had a loop where we say t starts at 0 and then t just continues, and at each step, at each t, we start to explore the grid more. And of course, we're going to keep a little queue of where we are currently at. And we put, the starting position in here. And then we just, as soon as we know that, okay, t is now high enough so that we can continue processing our neighbors, we will. In the beginning, t is 0, so we will only have this element in our queue. But we can't go anywhere because the neighbors are larger. Right? So we have to wait until t becomes 1, and then suddenly we can go to 1, and now 2 becomes a next neighbor, and so forth. So we need to have a queue that is sorted so that the minimum element is always in front of the queue. So we'll have to put in the height into our little queue here. In this case, it's 0 for the start. And in our loop, when we do our processing of our queue, well, we need to be able to get the minimum element. And how do we do that? Well, the easiest way to do it is with a heap. So we would have a min heap and yeah, a min heap. And what we then can compare is we can compare the min heap at its first position versus t, right? So if t is larger or equal than min heap, then we can start to continue exploring our graph. And that's exactly what we will do. We are going to need, as usual with these grid graph problems, we're going to need to have a function that returns us all the adjacent neighboring cells. This time we're going to include the height, because the height is going to be an important parameter that we need in our queue. And yeah, every time t increases, we start computing the next nodes. Now, what if let's say t is equal to 0? Let's say the value of the next cell here would be 12 instead of 1, right? Do we really want to loop 11 times over it? No, of course not. So if we discover that we cannot process any more elements that are in the heap, because the difference between t and the top of the heap is a large number, well, all we simply have to do is we just have to increase our t to match that value, so that when we loop over our t values here, we can have jumps in t, and we don't have to actually count all of the numbers from 0 to, I don't know, if there's a 20,000 is one elevation, we don't want to go all the way to 20,000, right? This was 70,000. We'd have to go to 20,000 to be able to reach the goal node. So that's a small optimization that we're also going to bake in. And that concludes, I think, the problem description or the solution, sketch of the solution. And I think we should just go into solving it. And we will do the runtime analysis after. And you can expect, because we're using heap, there will be a logarithmic part in that. Cool. So what's the first thing we'll do? Well, the first thing is, when we do these grid traversals, we need the width and the height of the grid. Width and height equals, so the length of the first row of the grid, that is the width, and the number of rows in the grid is the height. Grid, here we go. Now, we're going to need our little helper function, get neighbors, and we're going to pass in a height and, or do we pass in a height? I don't know. Yeah, maybe we pass in a height as well as the current position. And we're going to return an array of the neighbors here. And we will flesh that out in a second. All we know is we need to build this neighbors array. Now, the other thing that we need is that we're going to need to, how do you say? We need to, well, we need to explore the grid, right? So we need the core algorithm. And I'm going to use a breadth-first search for this. And I don't even know if we can use a recursive approach, or if that one would be easy to do. I think it would be much more complicated to have a recursive approach, thinking about it. So we should have, yeah, well, all we need to know what the start node is. We need to know what the goal node is, right? Let's define them as tuples, because we're going to use a visited set to ensure that we don't go to nodes where we already went. That's also a typical thing that we will do in our visited, in our matrix traversal or even graph traversal problems. So the start node, what is it? Well, it's at position 0, 0, and the goal node is at position width -1 and height -1. Now we have an n by n matrix here, right? So we could also just say that we take this as n, and then we don't have to deal with the width and height. But if somebody asks you a follow-up question, what if this is not a square matrix? Well, then you have to do the width and height bands. But yeah, for this problem, let's just use n. And yeah, now the next step is, well, we need our little processing queue, and we're going to use a FIFO for that, which is in Python the deck. And we're going to put, well, what are we going to put into this? Well, we're going to put our starting node into that, but we're also going to put the height of the starting node into that. Start. And the height of the start node is at grid position 0, 0, 0, right? So that's how we start. Then we'll have our main loop. So while we have elements to process, and by the way, it is guaranteed that we can reach the end. T just has to get large enough, and then we will reach it. There's no way that we're never going to reach it, since all elements in the grid are going to be numbers. Oh, yeah. So, by the way, these constraints, we don't care if all the elements are unique. That doesn't matter for our algorithm. That the height in the grid is the height or the elevation levels that they are bounded also doesn't really interest us. It's good to know that there's at least one node in the grid, right? Yeah. And of course, we need to keep track of our value t. So in the beginning, our value t is 1, right? So, well, so we've now built all of this up. I like to keep that ordered by length for some reason. You don't have to do that. And now, well, what do we do now? Well, actually, I made a mistake, right? We're not going to use a queue, are we? We're going to use a heap. So this is going to be a list. And in the beginning, we just add one element to it. So we don't need to heapify it. It's already a min heap because there's only one element in it. Maybe I should make that a little clearer. So we use min heap. And now what we have to check is, well, we can process elements from the heap as long as their height is smaller or equal to t. So while min heap at position 0, that gives us the first entry, but we also want to grab the height. So that is the first element in the first element of the first element in the min heap, that is the height value. So while height is smaller or equal to t, we can process it, right? So we're going to pop out the position, and that is heap pop on the min heap, and that gives us the position as well as the height. Now, what we have to do is, well, what do we have to do? We have to check if we've already visited that position. So if pos in visited, we're just going to ignore it. Otherwise, we're going to have to add it. Visited, add pos. And we don't care about the height in our visited set. We just care whether we've visited it or not. Right, so now, well, since we have not visited it before, we now need to check if pos equals goal, right? Then we can return our value t, because we've reached the goal when the water height is t. So that's our termination condition, and it's guaranteed to be reached. So we can actually say this while true. We could do that. Now, what else do we need to do? Well, we need to process the neighbors. And so what we'll do is we'll, for the height of the next height and the next position in get neighbors of the current height of the current position. What we can do is, well, actually thinking about, I don't think we need to pass the height for the neighbors, because we're not filtering in the get neighbors methods for height. We're doing our height filtering by using the min heap, right? We don't process, that ensures that we are processing smaller elements first. All right, we're doing the get neighbors thing, and we're going to add that to our little min heap, to our processing queue. So we're going to use heap push, and we're going to put that into our min heap. And what are we going to put to it? Well, an area of the height of the next position, right? And the next position itself. So that is that. Now, we have to, I talked about what do we do if t is, 0 or 1, and our next height position is large, right? Well, we don't want to loop as many times. Otherwise, it would be an n squared if we assume that the maximum height is n squared, right? We could have first cell 0 and all the other cells be the value n squared. So that would instantly give us like an n squared algorithm. Why do we want to do that? We don't. So what we'll do is, after exhausting all our options to process elements from our min heap, because the elements left on the min heap are larger in height, well, all we have to do is we have to set t to whatever the height is in the first element in our min heap, in our queue. I don't know if we should call it min heap or queue. What do you think? I think maybe we should stick with queue, because in all of the other graph problems we've been using a queue, a deck, or whatever. So this is really our queue, except it's a min heap. It's like a priority queue. That's what we should probably call it. Cool. So heap push, heap pop, right? So yeah. Now this should be the main logic, but we also want to flash out our get neighbors thing. So we'll do our usual. We iterate over the position of all the neighbors as follows in zip, and we're going to iterate from position. Well, we're going to pull out the x and y coordinate from the position tuple, and then we're just going to be x minus 1 and y, that is the left neighbor, x and y minus 1, y minus 1, that is the top neighbor. We also look at the left neighbor and at the bottom neighbor. So that'll be at y and at y plus 1. Right, so now we have to do a little check if nx smaller than 0 or nx larger or equal to n. That's out of bounds. We want to ignore it. Same for the y coordinate. And yeah, and if that all checks out, well, we just need to fetch the height. So the height is at grid position in y and x, because we're pulling out the row first and then the column. And then we just add it to our neighbors. So we take the neighbors array, append, and we're going to append a little array of the height. And the next position, of course, the next position is going to be a tuple of nx and y. Right, so that should be everything. We're going to look at the time and space complexity. Well, space I think is easier here to determine. Well, because we could have the example where, right, all elements are the same height. That means we are instantly adding all of them to our queue, all of the elements and all of its neighbors, etc. So the space complexity is definitely O of n times n, since we have a square grid. Sorry, space complexity is O of n times n. Now, in terms of time complexity, what are we looking at? Well, we are looking at in the worst case, we are adding all of the nodes to the grid, and we need to perform an n times n heap pop and heap push, right? So I think it's, so an upper bound definitely is O of n, where's my caret? There. Caret, character, not the carrot, the vegetable. Times log n times n. Yeah, I think that is an upper bound. Maybe if you think a little bit more about this, maybe you can tighten this even more. You know, is it even possible to have all the elements in here, and do we then even have to do the heap pop, heap push, and all of that? No, actually, I can think of a worst case scenario. So if you have all cells are 0 and the last one is maybe n squared, when you insert the first cell, then in the next iteration of this loop, you're going to add all of the elements to the queue. So you're going to have n squared heap push operations. And then when you want to process them, well, you're going to pop them out again. So I think this is an accurate and tight upper bound, I think. Yes, so I think that concludes the solution. Let's just check if we made any errors implementing this. Okay, that looks good. Now let's submit it. And ta-da! Okay, nice. Very good. So I'm pleased with this. I'm actually surprised how easy this is, but it kind of also shows that, well, if you know the other approaches of how to approach the graph problems from the LeetCode 150 list and the ones that we've done before in the other videos, This should not be difficult for you. The only twist is that you have to use a heap queue to keep the next neighbors in a kind of priority order. So yeah, I hope you will find this easy to implement as well, and I encourage you to do so.